Hello. This video includes information on temperature and reaction rates, reaction catalysts, and reaction mechanisms.
We're going to talk a little bit about the relationship between the temperature and reaction rate for a given reaction. What we look at when we relate temperature and reaction rate is what's called the Arrhenius equation. And our Arrhenius equation is K equals AE negative EA divided by RT. So let's talk about what all those variables mean. So this A here, okay, is a frequency factor, okay? It just has to do with how often are the reacting particles actually colliding into each other. And we know that reactions aren't going to take place unless the particles actually collide with each other. This E to the negative EA over RT, okay, that tells us the fraction of molecules that have enough energy to overcome that activation energy so that the reaction can actually take place. Now, when we go to calculate this fraction of molecules that have enough energy to actually react, we need to know what the temperature is, and we need to know what R is. And in this case, because we're dealing with energies, our R value for these kinds of problems is 8.314 joules per mole Kelvin. So if the temperature were to go up, the effectiveness of the collisions increases because more particles have enough energy to actually react to produce product. Now, if we look at this graphically, if we were to look at kinetic energy, temperature is a measure of average kinetic energy, and the number of molecules, okay, if we have a lower activation energy, more molecules are going to have enough energy to react. If we're looking at a reaction with a higher activation energy, less molecules have enough energy to actually react. Now, when we look at this graph, now we're looking at the distribution of kinetic energy among molecules at two different temperatures. So this first curve here, the red one, is when we're looking at a reaction at a lower temperature. If we're looking at a reaction at a lower temperature, the distribution of kinetic energy is kind of more compact. And only a small number of molecules underneath this curve here actually have enough energy to react. But if we increase the temperature, we see a distribution of kinetic energies that looks like this black curve here, where the distribution is kind of spread out a little bit more. So at a higher temperature, we have more molecules that can overcome that activation energy and actually carry out a reaction. So this graph here is telling us that as the activation energy decreases, the number of molecules with at least that amount of energy increases. So if we decrease the activation energy, the reaction is going to go faster. Okay, and this reaction here tells us that when we increase the temperature, more molecules have enough energy to overcome that activation energy. Now, reaction mechanisms. When we look at reactions, oftentimes there is a sequence of steps that explain how the reaction actually occurs. And that's what we mean when we talk about a reaction mechanism. And each step in this sequence of steps is called an elementary reaction. And it represents a singular molecular event or a singular reaction. So if we were to look at the decomposition of ozone, okay, O3 is ozone. Ozone decomposes into oxygen. This is an overall reaction, a net reaction. In reality, it's believed that it occurs by way of a reaction mechanism, a sequence of steps where ozone breaks down into oxygen molecules and oxygen atoms, and then those oxygen atoms will react with more ozone molecules to produce oxygen. The sum of the elementary steps will always equal the overall reaction. So if we were to add these two reactions together, we would get 2O3 yields 3O2. The oxygen atoms are going to cancel out. When we look at these reaction mechanisms, we need to talk about what's called molecularity for the elementary steps. And when we look at the molecularity of the elementary steps in a reaction mechanism, it's the number of reactants that are present. So we can have what are called unimolecular elementary steps, meaning there's only one reactant. We can have bimolecular elementary steps, which means there are two reactants. Or we can have termolecular elementary steps where we've got three reacting particles. And having three reacting particles, having termolecular elementary steps is unlikely, because in order for a termolecular step to take place, all three particles would have to come in contact with each other at the same time, which is unlikely. They'd also have to collide with each other all at the right orientation at the same time, which is unlikely. And all three particles would have to have enough energy so that when they collided, and if they collided in the right orientation, they have enough energy to actually react. Pretty rare that you would have that happen. So let's look at these three just general reactions. Okay, we want to focus on the reactants, the number of reactants in each of those elementary steps. For the first example here, is it unimolecular, bimolecular, or termolecular? For the second one, B, is it unimolecular, bimolecular, or termolecular? And in the third one, C, is it unimolecular, bimolecular, or termolecular? So the first one is termolecular, 1, 2, 3. Unimolecular, right? We've got one reacting particle. What would the third one be? Bimolecular. When we look at these molecularities, okay, the rate law is based off of the stoichiometry in that elementary step. So if we look at a unimolecular elementary step, it's first order. Okay, so rate equals K times the concentration of A. If we were to look at bimolecular, well, it could be A reacting with B, or maybe it's A reacting with A. Okay, they can react with, two species that are the same. So it would be rate equals K times the concentration of A times the concentration of B, or rate equals the concentration of K times the concentration of A squared. Okay, remember that to figure out the order of the overall reaction, it's the sum of the individual orders for the reactant. So 1 + 1 is 2, or 2, same thing. If we're looking at termolecular, it could be A reacting with B, reacting with C. Maybe we've got A reacting with 2B, or maybe we have 3 A's reacting together. Either way, we've got 3 reactants. It's termolecular. So our rate laws could be K times ABC, K times A, B squared, K times A to the third. Now, let's look at rate laws and reactions. So when we talk about elementary reactions, Okay, elementary reactions are reactions that occur the way that they're written. There aren't steps in the mechanism. They occur just the way they are. And if that's the case, then we can use the stoichiometry in that reaction to figure out the rate law. Okay, so unimolecular is first order and bimolecular is second order. Termolecular, rare, but that would be third order. But most reactions are a lot more complex than that. Even though we write down an overall reaction, the reaction actually takes place in a series of steps. It has a reaction mechanism. So they don't occur as written. They're essentially written as a summary of the steps in the mechanism. So they're carried out in a series of elementary steps. The reaction rate is dependent on what's called the rate determining step, which can be just shorthanded, so we have to write it all out all the time, RDS. Okay, it's the slowest step in a reaction mechanism. In other words, reactions can't go any faster than the slowest step in its reaction mechanism. So let's look at an example. We have nitrogen dioxide reacting with carbon monoxide to produce carbon dioxide and nitrogen monoxide. At 25 degree or 225 degrees Celsius, we're told that the rate law is rate equals K times the concentration of nitrogen dioxide squared. This rate law doesn't match up with this equation for two reasons. We only have one nitrogen dioxide instead of two, and carbon monoxide isn't in the rate law. So this reaction must take place by way of a reaction mechanism, must take place in a series of steps. So the above reaction is not consistent with a single step mechanism, but is consistent with this. Now, you would never be asked to figure out what a reaction mechanism is, but you could be given the reaction mechanism and then you have to do things with it. So it's proposed that this reaction takes place in two steps. So we've got the first step here, and then we've got our second step here. And it tells us, you would not know, it tells us that the first step is the slow step in the mechanism. It's the rate determining step. Well, what we can do with that is we can say, well, the rate of this reaction is equal to the rate of the rate determining step in the reaction mechanism. Well, this is the rate determining step. It's bimolecular. So the rate equals K times the concentration of nitrogen dioxide squared. So this rate law matches the rate determining step in the mechanism for this overall reaction. The fast step is so fast that it's not going to be controlling the rate. The rate of the overall reaction here can't be any faster than the slowest step. The fast step isn't going to affect the rate. So when we look at reaction mechanisms, multi-step reactions, we want to know what the rate determining step is, and then we can use the molecularity, the stoichiometry, in the rate determining step to determine what the rate law is for that particular reaction. So let's look at another example. Let's say that we're given this information. Again, it's not something that we can figure out, but we'd be given it and asked questions about it. So we have the first step in the reaction mechanism here. We have the second step in the reaction mechanism here. And it tells us that the first step is a slow step. Okay, well, we want to figure out a couple of different things. The first thing, it doesn't give us the overall reaction like it did on the last slide. So we want to figure out what the overall reaction is. And whenever we do that, The coefficients in that reaction are always the smallest integers. So in other words, we want to add these two steps together. We want to cancel out anything that's either produced in one step and consumed in another step, or consumed in one step and produced in another step. And then once we do that, we want to decide what the overall rate law will be. And we figured that out from the rate determining step. Let's look at the first part. What's the overall reaction? Well, we're going to add these reactions together. Okay, so we've got hydrogen plus ICl plus ICl plus HI. We're just adding all the reactants together. Yields HCl plus HI plus HCl plus I2. We're just adding all the products together. Now, when we add up the two steps in the reaction mechanism, we have HI here, which is produced in the first step. And we have HI here, which is consumed in the second step. It's an intermediate. We don't include intermediates in our overall reaction. We just cancel them out. So this is the overall reaction for this mechanism. But because this reaction takes place in a series of steps, we can't say that it's a termolecular reaction. We're not just going to use this stoichiometry here, this molecularity, to determine what the rate law is going to be. We're going to look at the slow step. What's the intermediate? Well, the intermediate is what's produced in one step and consumed in the other steps. That's HI. And then to figure out the rate law, we're going to look at the molecularity of the rate determining step. Just comes from the stoichiometry right here. Since this is our rate determining step, the slow step, our rate expression, our rate law will be K times the concentration of ICl times the concentration of hydrogen. Doesn't matter that the order here is backwards from the order here. It doesn't matter what order we put them in. But we've got a 1 here, which means the reaction is first order with respect to hydrogen. And we have a 1 here, which means it's first order with respect to hydrogen monochloride. It's a second order overall reaction. But this rate law doesn't match up with the overall reaction because the reaction takes place in multiple steps. Let's look at reactions that have what are called equilibrium steps in them. And we're going to spend a lot more time in the next couple of chapters talking about equilibrium. We're just going to talk about them very generally here. When we talk about equilibrium reactions, they're reactions in which they're reversible, meaning that the reactants can produce products, but then the products can reproduce the reactants we started out with. They're reversible. They can go in both directions. Okay. And when they're at equilibrium, the rate of the forward reaction equals the rate of the reverse reaction. So let's say that we're given a reaction mechanism that has 2 steps in it. And we're told that the second step is the slow step. Okay, well, what we need to do is we need to look at the molecularity of the slow step, but we need to notice that the reactant, one of the reactants in the slow step, was actually produced in the fast step. These cancel out. They're produced here, they're consumed here, they're intermediates. We're not going to include them. Now, when we go to write the rate expression, let's look at the first reaction first, and we'll look at it in the forward direction. Well, rate equals K times the concentration of NO times the concentration of Cl2. Okay, the first reaction in the forward direction. But look at the arrow here. The reaction also goes in this direction. So we'll just say rate prime, okay, we're talking about in the reverse direction, will equal a new constant times NOCl2. And the rate of the forward reaction equals the rate of the reverse reaction, because we're looking at a reversible reaction at equilibrium. So these two rate laws summarize the first step. Now, if we look at the second step, okay, it's the molecularity. So rate equals K times the concentration of NOCl2 times the concentration of NO. Now, we're going to have to do a little bit of manipulating with this. The rate of the forward reaction equals the rate of the reverse reaction for an equilibrium reaction, for a reaction that's reversible and at equilibrium. So for the forward reaction, we can substitute in the rate law. And for the reverse reaction, we can substitute in the rate law. Now, NOCl2 is an intermediate. Intermediates are never found in a rate law. So let's kind of manipulate this equation. We're going to solve for the intermediate. So we're going to divide by K prime. Okay, and we get this here. What we're going to be able to do now is a substitution. We're going to look at the rate determining step, which has the intermediate in it. Intermediates are never in a rate law. So we're going to substitute NOCl2 with all of this because they're equal to each other. The overall rate law will equal K2 times K1 over K prime times NO times Cl2 times NO. Now, we've got NO here and NO here, so we could just consolidate them and write NO squared. And since K2, K1, and K prime are all constants, we can kind of write them all together as their own little constants. And this is our rate law. And this actually matches up with the molecularity in the rate determining step. Let's look at this reaction. Okay, this is the overall reaction. Okay, we're going to kind of go back to the beginning for a minute. See if you can use this data to figure out what the rate law for this reaction is. So this is going back way to the beginning of the chapter. Okay, we want to determine what the order is for each of the reactants. So if we were to look at, let's say, trial 1 and trial 2, NO stays constant. We double H2. How does doubling this concentration affect the rate, and what order is hydrogen? Then if we look at trial 3 and trial 4, we're holding hydrogen constant. We're doubling NO. See how doubling NO affects the rate, and figure out the order for NO, and then write your rate law from that data. Now, once you decide what the order is, you want to calculate K for the reaction, including the units. So for M, if we double the concentration, it quadruples the rate. So nitrogen monoxide is second order. Okay, do the same thing for hydrogen. We double the concentration, it doubles the rate. What does N equal? For the second one, N equals 1. We double the concentration, it doubles the rate. Hydrogen is first order. So we know what M is, we know what N is, we know our rate law. Now, look at this. This rate law does not match the molecularity of the reaction we're given. That means that this reaction must take place in a series of steps. Okay, and that's the next thing we're going to go over. So we want to calculate K. Pick any trial you want, plug in the concentration for NO, the concentration for H2O, and the rate, and you're calculating K, and you want your units to go along with it. So 5.0 times 10 to the third liters squared per mole square minute. Again, doesn't matter whether you pick, the data from trial 1 or the data from trial 2 or the data from trial 4, doesn't matter. They just have to be from the same trial. So don't pick, a number from trial 1 and then a different number from trial 2 and then a different number for trial 3. They're not related to each other. Okay, whatever trial you pick, plug in the rate, plug in the concentrations. Now remember, you have to double the concentration of NO, and you're raising the concentration of hydrogen to the first power. So don't forget to do that. You're doubling the number and you're doubling the units. Okay, now moles per liter cancels out with your moles per liter. You're left with 1 over minutes divided by moles squared divided by liters squared, and we just take the reciprocal of that fraction in the numerator. So that's where these units come from. And those are the units that we would have for a third order reaction. Now, this rate law doesn't match the molecularity in this overall reaction. So let's tie in what we just did with reaction mechanisms. We're told that this is a proposed mechanism for that reaction. It's proposed that this reaction takes place in 3 different steps. Okay, we want to figure out what the rate law is based on this reaction mechanism. Well, we look at the rate determining step, which is step 2, and we look at the molecularity in step 2 to figure out what the rate law is. But the problem is that rate laws can't have an intermediate in them. So we're going to have to look at the rate for this equilibrium expression here in order to figure out what the rate law is overall. So let's go through that together. Since step number 1 is a reversible reaction, the rate of the forward reaction equals the rate of the reverse reaction. So K1 times nitrogen monoxide squared, that just comes from the reactants here, equals K prime times the concentration of N2O2, that just comes from here. And again, it's a reversible reaction that's at equilibrium. So the rate of the forward reaction equals the rate of the reverse reaction. Then we want to isolate the intermediate because that's what we're going to be canceling out. So we're going to divide both sides by K prime, and that gives us our intermediate kind of isolated from itself. And then we'll look at our rate determining step. So when we look at step 2, which is the rate determining step, rate's going to equal K2 times N2O2 times H2. But again, we can't have an intermediate in our rate law. So what we'll do then is instead of writing this, we're going to substitute in all of this. They're equal to each other. We can do that. So we're going to take all of this and we're going to substitute it in here. And that's going to give us our overall rate law. Okay, now this is actually all constants. So we can just kind of put it all together as one constant. Equals N2 or NO2 times H2. And that's exactly the same thing that we came up with from the data that we were given in the first part of the problem. Just using reaction mechanisms instead of data to figure out what a rate law is. Last thing we need to do in this chapter, and then we're going to take a break, I promise. So we have a potential energy diagram here. Here are our reactants. Here are the products. Now the products have less energy than the reactants had, so the reaction's exothermic. If we knew actual numbers, we would just take the products minus the reactants, and that would give us our delta H value. It would be a negative number. We just don't know the actual numbers. And the red curve here represents an uncatalyzed reaction. So the reactants have to have this much energy in order to get to this transition state where we're breaking bonds and rearranging atoms and then making new bonds to produce our products. What catalysts do is they speed up chemical reactions. And the way that they do that is by changing the reaction mechanism in such a way that they decrease the activation energy. And if you need less energy to get that reaction to proceed, the reaction is going to go faster. Now, there are a couple of different types of catalysts. There are homogeneous catalysts, okay? And we call them that because they're in the same phase as the reactants, okay? And they are going to be consumed in one step and produced in another step. So here's an example of an uncatalyzed reaction. Okay, we looked at this reaction already, and we said that oxygen atoms were intermediates. Well, we can make this reaction go faster by adding a catalyst. Like nitrogen monoxide is a good catalyst here. So if we add in nitrogen monoxide, it actually changes the reaction mechanism. Now, the nitrogen monoxide is consumed in this step, but it's reformed in the last step. So it's not part of the overall reaction. And by definition, that's what a catalyst is. And since the nitrogen monoxide is in the same state as everything else, it's a homogeneous catalyst. Now, we still have the oxygen atoms here and the oxygen atoms here, so they're intermediates, but we've added in a catalyst which has changed the reaction mechanism, which lowers the activation energy and makes the reaction go faster. So nitrogen monoxide in this mechanism is considered to be a catalyst. Now, chlorine in hydrofluorocarbons are also catalysts of this reaction, where ozone in our atmosphere is broken down into oxygen. Now, heterogeneous catalysts are named because the catalyst is in a different phase than the reactants. And typically, heterogeneous catalysts are solids. They don't always have to be, but they're typically solids. And essentially, there are 4 steps that take place when we look at heterogeneous catalysts, okay? There's the step where the reactants come in and kind of attach themselves to the solid catalyst. Then we have the reaction actually taking place on the surface of that catalyst. And then we have the products being released from the catalyst. But heterogeneous catalysts are typically solids that are in a different phase than the reactants are. They do the same kind of thing, though. They lower the reaction rate by changing the mechanism of the reaction. Now, catalytic converters, if you know anything about cars, okay, cars have catalytic converters in them. That's essentially a type of heterogeneous catalyst that helps to break down all of the things in our fuel so that we can release things like oxygen and carbon dioxide and water from our tailpipes, instead of things like carbon monoxide and nitrogen monoxide, which are environmental hazards. Just an example of a catalyst.